Assalamualaikum warahmatullahi wabarakatuh. Okay, now we continue our fluid mechanics in topic 2 based on part B. Okay, so more part B, so I will discuss more on hydrostatic pressure and buoyancy. Okay, so we have discussed in part A is more on pressure. Okay, now we go through in hydrostatic pressure and buoyancy. Okay, what is hydrostatic force? Okay, hydrostatic force in plane surface. So we'll learn the hydrostatic force in plane surface. Okay, a plate exposed to a liquid such as a gate valve in a dam, the wall of a liquid storage tank, or the hull of a ship at rest, okay, is subjected to fluid pressure distributed over its surface. Okay, on a plane surface, the hydrostatic force form a system of parallel forces, and we often need to determine the magnitude of the force and its points of application, which is called the center of pressure. Okay, so this is more on hydrostatic force. So we look at the concept here. Okay, so when analyzing hydrostatic force on submerged surface, so in submerged surface, okay, so the atmospheric pressure can be subtracted for simplicity when it acts on both sides of the structure. So maybe this is the forces in submerged surface with the horizontal here, okay, and the force is vertical. Okay, when the hydrostatic force here, okay, with the vertical here, okay, horizontal here, so the object, okay, based on the submerged in this liquid, so they have vertical, and the forces, hydraulic forces, is horizontal. So this is also this one, and based on this shape. Okay, so now we look at the concept here. Okay, when we have learned the variation of pressure with the depth, so now we look at this figure here. Okay, so when when the variation of depth is a h here, so they have the increase of pressure here. Okay, and the p atmosphere is open to the surface here. Okay, so we know that to get the pressure at the bottom here, so they must consider the p atmosphere. Okay, p atmosphere, and also the pressure gauge in this liquid. Okay, so it's also p atmosphere when it is submerged here, so they have no p atmosphere. So the hydrostatic force is must include the p atmosphere and also the the pressure gauge in this liquid. Okay, when analyzing hydrostatic force on submerged surface, the atmospheric pressure can be subtracted for simplicity when it acts on both sides of the structure. Okay, on both sides of the structure here. So the P atmosphere is considered, and also when P atmosphere is submerged, so they only have the P gauge only. Okay, so now we look at the hydrostatic force on inclined submerged plane surface. So when the plane surface here is inclined, okay, they have the the pressure at the center here. Okay, pressure at the center of this plane surface. Okay, so the pressure at the center is equal to pressure average. Okay, average. And we know that the force, okay, is considered at this part here. Okay, so the force resistance here is equal to pressure at the center times by the area. Okay, area of this plane surface. Okay, so the plane surface area of this, okay, actually this is the plane surface, so this we can look from the okay, plane view. Okay, so we know that the C is the centroid. Okay, and the CP here is the center of pressure, and the A is the plane surface of this area. Okay, so we know that from the water surface here, so we just get as the zero here at the surface. Okay, the level water surface here, until to get to the sea center here. So we get the YC. YC is the distance from the 0 here until to the centroid. Okay, so the YC here. Okay, and the Y here is the distance from the surface here until to the at the point here at the P is equal to, okay, pressure at the surface here. Okay, so P naught plus density of fluid times by the G times by the Y sine theta, because we have the sine theta here. Okay, at the sine theta, this one is sine theta. Okay, so the distance of the for the H is equal to Y sine theta. Okay, so actually the pressure at the centroid of a surface is equivalent to the average pressure on the surface. Okay, so we know that the pressure at the distribution actually for this key concept plane surface of area, so we just look through this. Okay, pressure for this volume here. Okay, so the pressure distribution. So now we look at, okay, for this concept here. Okay, this is the free surface. Okay, this is water level here, so there's the free surface. Okay, so this is the centroid of the surface here. Okay, so we get the HC here. Okay, and at the P average is equal to PC. Okay, so P average, okay, P pressure average is equal to pressure at the centroid. Okay, at this centroid here, so it's equal to P, consider of the P atmosphere plus and the P gauge in this with this depth. Okay, with this the variation of depth. Okay, so with the variation of this depth. Okay, we have learned. Okay, so that's why we get the density of fluid times by the G times by the H. Okay, actually H is the distance from the water surface here until at the centroid, so we get the C. Okay, so we get the C here. Okay, now we know that the Fr is the force resistance. Okay, force resistance that occur to this plane surface. So we know that the equation of this force resistance is P naught is actually pressure. Okay, pressure at this, okay, at this centroid here. So no need to worry about this one. So you must know that the P naught, okay, pressure at the center times by the area. Okay, so just remember this equation. Okay, pressure, okay, force resistance for this plane surface. Okay, so it's equal to pressure average times by the area. Okay, so we know that the pressure average or PC, we use this equation. Okay, because this is for plane surface that incline. Okay, just only for inclined submerged plane surface. So we have the sine theta here. Okay, so they have the sine theta. Sine theta actually for this, okay, this angle here. Okay, so the HC, so we get the YC. Okay, HC is equal to YC times by the sine theta. Okay, so that's why the GHC, so HC is equal to YC sine theta. Okay, and times by the area. Okay, the centroid from water surface, the centroid from the water surface HC is YC times by the sine theta. Okay, so we know that the YC is actually, we get the from the water surface here, so we get at the centroid. So the length of the centroid for YC. Okay, so now the magnitude of the resultant force. Okay, so the magnitude of the resultant force acting on a plane surface of the completely submerged plane in homogeneous is constant density. So fluid is equal to the product of the pressure PC at the centroid of the surface and the area A of the surface. So we know that actually this is the force, okay? Force resultant acting at the plane surface here is equal to pressure at the centroid times by the area, okay? So we know that this is the YC and this is the YP, okay? Okay, YP is the distance from the surface until to the resultant force. Okay, so this is called resultant force, this is called magnitude. Okay, so the magnitude of the resultant force is called YP. Okay, so the YP here, magnitude of the resultant force is the length to get the YP. Okay, so to get the YP, so we must know that the moment I see at the centroid, okay, divide by the YC is the distance here until to at the centroid, okay, times by the A plus the YC, okay. So we know to get using the IC here, okay, so you must refer to next slide, okay, the IC. So we use this one, okay, inertial formula, okay. So if the plane surface, the plane is rectangle, so use the I inertia is using this equation. If the plane surface is circle, so you use this C, okay. Okay, no need to worry. So this equation will give in test or in your final. Okay, so just don't worry about this one. So you just must remember this equation. So this equation is also given to you. Okay, the YP and so on is given to you. So you must know how to get the I here. Okay, so now we look at the hydrostatic force on horizontal submerged plane surface. So this is horizontal. Okay, the previous slide is inclined. Okay, so now we look at the horizontal submerged plane surface here. So this is plane surface, horizontal and submerged to liquid to the fluid. So we have the YC is equal to HC because this is horizontal. Okay, and we know that the force resistance here, okay, force resistance is based on the centroid here, okay, and we know that the distance from the plane surface here with the horizontal is xc, okay, x is the length to the center. So calculation for magnitude, okay, for magnitude, location and direction of a resultant force on horizontal submerged plane surface are same as inclined plane surface. However, distance of HC is equal to YC because XY coordinate system is parallel to fluid surface. Okay, so the magnitude, okay, the location, YP, YC, okay, the direction of resultant force, how to get the FR, okay. So it's the same as inclined plane surface, but to get the distance of HC is equal to YC because XY coordinate system is parallel to fluid surface. Okay. So this is a concept for the vertical submerged plane surface. So this is hydrostatic force. Hydrostatic force here, hydrostatic force, okay, to vertical submerged plane surface. Okay, so the hydrostatic force here is, this is the CP is the center for the hydrostatic force, and the C is the centroid, okay, centroid of this plane surface. Okay, so they have the YP and the YC. So this is based on vertical submerged, so the hydrostatic force or force resistance, okay. So you can use hydrostatic force or you can use force resistance. So this is the same concept, the same meaning for this hydrostatic force, okay. So calculation for magnitude, location and direction of resultant force on vertical submerged plane surface are also same as inclined plane surface, so they're the same, okay. So the YP, YC, so this is based on the vertical submerged plane surface. Okay, so now we look at example here. So the example here is using the incline, okay, incline plane surface. So using the rectangular gate. Okay, so when using the rectangular gate, so you must refer the inertial force using the rectangular. Okay, so a rectangular gate, this one, okay, with 5 meter that leans against the floor with an angle of 45 degrees Celsius. Okay, 45 degrees with the horizontal. Okay, with the horizontal here. Okay, is to be opened from its lower edge by applying a normal force at its center. Okay, so they have the force here, the hydrostatic force here occur to at this part, and the force here. Force here is at the center here. Okay, this is center, this is CP. Okay. Okay, so now we look at the solution here. Okay, so consider figure here. Okay, so you just consider figure below here. So we add the surface here. Okay, you just use the dot line here. Okay, until at the surface here. So we just put as the 0 here. Okay, and here, and so we know that this is the YC. Okay, so this line is the YC at the center here, center of the plane surface here, and the YR is the distance from the surface until to the hydrostatic force. So we get the YR here. Okay, YR, or you can use SYP. Okay, so YR or YP. Okay, is the same. Okay, so YR or YP. Okay, so you can use. Okay, and we know that it's 1.2 and this one is 3 meter. Okay, so this is 45 degrees. Okay, so now we look at the magnitude. To get the magnitude of resultant force. Okay, to get the magnitude, so this is YR or YP here. Okay, so first you must know that the hydrostatic force, the equation for hydrostatic force is rho GHCA. Okay, actually this is based on the previous slide that is inclined. Okay, so you can use this actually for this. Okay, from the P average area here, so you can get the DC. So okay, from this incline here, so you get the value here. Okay, so you get density times by the G times by the HC times by the A. Okay, actually is the pressure at the center times by the A. Okay, rho GH is the pressure at the center here. Okay, the pressure at the center here. Okay, pressure at the center here, rho GH. Okay, so if the P naught, give you the P atmosphere. Okay, if not, so we just use the rho GHC A. Okay, so that's why we use the equation here for hydrostatic force. Okay, to get the HC, okay, actually HC is 3 over 2 times by 1.2. HC is at the part here. Okay, at the center of the, from here. Okay, HC to get the S until to the F. Actually HC is this one. Okay, so HC. Okay, HC from the water surface until to at the centroid of surface. Okay, so that's why you must find the HC. Okay, the HC. So the HC until at the surface here. Okay, so you must find the HC. Okay. Okay, from the surface here until to the centroid. So you get this HC. So that's why you get the HC is 3 is at the 3 meter. Okay, divide by 2 because it's the half of this, because it's half of this plane. So we get the 3 divided by 2 plus 1.2. So we get 2.7 meter. Okay, so now we look at the area. Okay, area of the rectangular. So rectangular, B plus H. Okay, so we know that the H, okay, H is, the B is given as 5 meter, okay, and the H 4.24. So how you get the H here? Okay, H actually is you get from the, sorry, so you get from the here. Okay, so you get the X here. So sin theta, sin 45 here, so you want to get the X here. Okay, actually to know that the X, until X, the X here. Okay, okay, the part here is the X. What is the X here? Actually, what is the X? Okay, okay, that's why X, the 45 degree is 3 meter. So X is 3 divided by sine 45. Okay, so you get the value of, okay, so you get 4.24. Okay, so that's why you get the 4.24. You just use as the H here. Okay, so we know that the area is 21.2 meters squared. Okay, so now to get the the hydrostatic force here, so you just put the value, the density of water. Okay, so you just use to this here, density of water times by the HC is 2.7, okay, times by the area. So you get the hydrostatic force based on this value. Okay, so this is the concept for the calculation. So to get the magnitude, okay, to get the magnitude of resultant force or hydrostatic force. Okay, so you know the magnitude here 2.7. Okay, and the X here 4.24. So you get the hydrostatic force. Okay, now you look at the location of resultant force YR. Okay, so we use this equation. Okay, because this is for location, you want to find the YP or YR. Okay, YP or YR. Okay, so use this formula, the equation here. So we use the rectangular. So use the rectangular. So we use this rectangular. Okay, so use rectangular based on this. Okay, AB power of 3 divided by 12. So we get the here. Okay, just put the, okay, the length and the, okay, the length of the width and the length of this plane surface. So you just put 5 times by the 4.24 power of 3 divided by 12. So you get the value here. Okay, so now you want to find the YC. Okay, we don't know what is the what is the value for the YC. Okay, so you just put, you get the YC here, and we know that the angle here and the HC. So we know the HC is 2.7. Okay, so you must find the YC. So YC, so you get 2.7 divided by sin 45. So you get the YC is, okay, so you get the 3.82. Okay, 3.82. Okay, so you get the here. Okay, to get the YC. So the YC is 3.82. So just to get the YP, so you use the equation here. Okay, equation here. So you get the value of 4.21. Okay, so the hydrostatic force is more complicated, so you must understand and you must calculate step by step. Okay, so now we look at so until at this part. Okay, so you can understand. Okay, from magnitude, find the magnitude. Okay, find the hydrostatic force, and then you find the location of resultant force or hydrostatic force, YP or YR. Okay, So YP OYR. Okay, so this is the location of hydrostatic force that you must calculate. So now we look at example 2.12 here. Compute the resultant force acting on plane A. Okay, they have the plane A and the plane B. So plane A is vertical plane surface and the plane B is the incline. So they have two. So you must have two calculation using the vertical force here, hydrostatic force, and the vertical plane surface and the inclined plane surface. Okay, so the dimension of panel A is 2 meter times by 1 meter, and the dimension of panel B is 2 meter times by 0.5 meter. Locate the center of pressure. Okay, you want to find the Y to get the center of pressure here. Okay, so you must calculate the panel A. Okay, you must calculate the panel A first. Okay, so vertical distance from water surface to centroid. Okay, so we know that from the water surface here, from surface to centroid, so we know that the HC. Okay, the HC. So we know HC is 1.5 times by the, actually this one is 1 you get from this one, 2 divide by the 2, so you get the 1. So that's why you get 1 here. Okay, so HC is 2.5 meter. Okay, and the submerged area of this plane surface is 2 meter times by 1 meter, so you get the 2 meter squared. Okay, so resultant force, okay, you use this equation. Okay, actually the resultant force is also rho GHC times by A. Okay, so you use this to get the hydrostatic force, resultant force, or hydrostatic force. Okay, so you no need to confuse. Okay, actually resultant force or hydrostatic force. Okay, so you find we know that is the water, so use the density of water is 1000, so you can, or you use the density of water HCA. Okay, so you just 1000, okay, times by 9.81, okay, times by the HC is 2.5, and times by the area 2. Okay, so you get the, from this one, so you get the value of hydrostatic force. Okay, so now you look to get the YP, so you must use the inertia here. So inertia here, because it's a rectangular, so use this equation for inertia. Okay, I is equal to 1 times by 2 power of 3 here, so you get the value here. Okay, so distance from water surface to centroid parallel to panel. Okay, so the location of the center of this pressure. Okay, so you use this one. Okay, YP is equal to IXC times divided by YC times by the A plus the YC. Okay, so you just put the value here. To this part here, YC is 2.5 times by the 2 and plus 2, so you get the value here. Okay, so the value for this YP, okay, so you just type the value here. So 0.667 divided by 2.5 times by 2 and plus 2.5. Okay, so you get 2.6334 meter. Okay, so you get the value of YP. So now we look at the panel B. Okay, after you finish the panel A, okay, so use the panel B here. Okay, panel B is inclined. Okay, inclined surface. Okay, so you find the vertical distance for water surface here. Okay, to get the YC. Okay, to HC. Okay, so 1.4 meter times plus sine 45, okay, and times by the 1, 2 divide by 2, so you get the 1 sine theta here, so get the value here. Okay, submerged area of this inclined surface, so you get the here. Okay, and the resultant force, you get the, this actually is density. Okay, density of water times by the G times by the HC times by the area. So you get the value of this one, and then you get the value of this one. Okay, so moment of inertia, this is also the rectangular, so use the AB power of 3 divide by 12, so you get the value of 1 meter power of 4 here. Okay, so distance from water surface to centroid parallel to panel, so you must find the YC. Okay, because this is inclined. Okay, so you must have the YC also. Okay, so from this one, so you must know the YC. Okay, so YC is HC. Okay, divide by sine theta. Sine theta is 45. Okay, so you get the value of this one. Okay, 2.980. Okay, so the location of the center of the pressure, so you just put the value here. Okay, until you get the YP is from the water surface. Okay, so that's all for this solution for this example. So now we look at the other example 2.13 here. So the compute the magnitude, okay, compute the magnitude of the resultant force or hydrostatic force on the indicated area and the location of center of pressure. Okay, so this is the, okay, the plane surface here is inclined. Okay, so you look at the here, the solution here. Okay, so we know that this is one. Okay, so you must know that the, okay, the inertia that you will use. Okay, the HC. Okay, at HC is you can find from this 0.4 meter. Okay, to get the HC. Actually, this is center. Okay, so you must have the, until to this part here. Okay, so that's why you get HC is 0.46 meter. Okay, plus, okay, they have 0.1. Okay, they have the length here 0.15. Okay, plus the 2 times by 0.51 divided by 3. Actually, 2/3 times by this, because this is triangular, so you must find the half of this triangular is 2/3. Okay, so you get the 3 times by the 0.51. Actually, it's the mathematical. Okay, actually the mathematical for this triangular to get the length from this triangular. So you get the this one and times by the sine 40, because this is 40 and this is 50. Okay, so you get the, this is 40. Okay, so you get the sign here, so you get the HC 0.775 meter. Okay, and the submerged area, so you get the submerged area here is triangular. Okay, the triangular is 1/2. Okay, plus the 0.51 and sorry times by 0.51 times by 0.76, so you get the area of this surface. Okay, and you get the hydrostatic force or resultant force using this equation. Okay, so you get the value of this one. Okay, so now we look at the magnitude. Okay, to get the y r or yp. Okay, y r or yp actually. Okay, so use this equation inertia. So use the, because this is a triangular, so you must use the BH3. So you must use the BH, this one, based on the triangular. Okay, and then you put all the value until you get the 0.0028. Okay, So and put all the YC to get the YC. So you must know the sine theta here and you get the 1.206. Okay, and put all the value to this equation. Okay, so you get the location of the center of pressure from the water surface. Okay, so you get the YP or YR is 1.218 meter from the water surface. Okay, now we look at the buoyancy and stability. Okay, so the buoyancy and stability, so the force that tends to lift the body is called the buoyant force, and it denoted by FB. Okay, so hydrostatic force we use as FR or resultant force or hydrostatic force, so we use the FR. Okay, for the buoyancy force we use the FB. Okay, so the buoyant force is caused by the increase of pressure in a fluid with depth. Okay, so the difference between these two forces is a net upward force, which is the buoyant force. Okay, so the FB in the fire FB is buoyant force. Okay, is equal to F bottom here. Okay, minus by the F top. So this is the top, this is the bottom. Okay, for balancing. Okay, so they must have the force from the bottom and they must have the force from the top. So that's why we get this one. Okay, for buoyant force. So F bottom minus by F tops. Okay, so the F bottom here is the density of fluid. Okay, density of fluid times by the G. Okay, times by the S plus H. Actually, S plus H is the distance, okay, from the water surface here until to this area here to get the H here. So you get the S plus H times by the A. Okay, and the F top here is the density of fluid times by the G times by the S. S is the distance here. Okay, times and by area. Okay, area of this surface, the body. Okay, so the body. So you get the FB buoyant force is equal to density of fluid times by the G times by the volume. Okay, so you just remember this equation. Okay, times by the volume. Okay, so where V is HA, okay, is the volume of the plate. Okay, but the relation, the density of fluids times by the G and times by the V is simply the weight of the liquid whose volume is equal to the volume of the plate. So we conclude that the buoyant force acting on the plate is equal to the weight of the liquid displaced by the plate. Okay, not that the buoyant force is independent of the distance of the body from the free surface. So it is also independent of the density of the solid body. Okay, so this is the free body surface here. They have the object here. Okay, submerged in the fluid. Okay, they have the object, the weight of this object. Okay, weight of this man. So we call the weight of object, and they must have the force. Okay, the buoyant force. The must have the force that balance the body of this person. Okay, so they must the free body diagram. So they must have the weight of object. Okay, the downward of the arrow here, and the upward arrow is the FB. Okay, so we use this concept for buoyant force. Okay, so now we look at this is also considered an arbitrary shape solid body submerged in the fluid. It rests and compare to its body of fluid of the same shape. Okay, so they have the same shape here. This is the solid, but this is the fluid. Okay, so the concept for the FB and the W is also the same. Okay, so they have must have the weight of the object and must have the force buoyancy of the solid and also the fluid. Okay, the buoyant forces acting on these two bodies are the same since the pressure distribution, which depends only on depths, are the same at the boundaries of both. So the imaginary fluid body is in static equilibrium, and thus the net force and net moment acting on it are zero. Okay, so therefore the upward buoyant force must be equal to the weight of the imaginary fluid body whose volume is equal to the volume of the solid body. Okay, so the further the weight and the buoyant force must have the same line of action to have a zero moment. So this is called Archimedes principle. So if in your test or in your final ask you to explain briefly about Archimedes principle, okay, so you can explain this theory, okay, and you can also sketch the diagram or this figure to explain more on Archimedes principle. Okay, also now we look at this also is the concept for floating bodies. Okay, so for floating bodies, the weight of the entire body must be equal to the buoyant force, which is the weight of the fluid whose volume is equal to the volume of the submerged portion of the floating body. So that is of uniform density, its weight W also acts through the centroid. Okay, so we use this equation. Okay, so this equation must go through the buoyant force is equal to weight. So the buoyant force, density of fluid times by the G times by the volume of submerged is equal to density average of the body times by the G times by the V total. So we get the FB is equal to W is also V volume, okay, submerged, divide by the volume of the total body, okay, of the weight, and density average of the body divided by the density of fluid. So it follow from this discussion that a body immersed in a fluid, so the one here, okay, remains at rest and at any point in the fluid when its density is same to the density of the fluid. So the two this part 2 sink to the bottom when its density is greater than the density of the fluid, and the 3 rises to the surface, okay, the rises to the surface of the fluid and floats when the density of the body is less than the density of the fluid. Okay, so this is explanation about this object. Okay, so maybe in your test or in your final ask you to explain about this object, so you can explain about this theory. Okay, so this is more on floating bodies. So now we look at the example 2.15. Okay, so figure below shows a crane is used to lower weight into the sea with the density water. Okay, and determine the tension of the rope of the crane due to the rectangular, and this is the volume here. Find the suspended when it is suspended in the air and when it is completely immersed in water. So you must find the tension. Okay, so this is suspended in the air. So this is completely immersed in water. Okay, so now first you must find the suspended in the air. Okay, so you must have the for equilibrium. Okay, they must have the weight here for this block concrete, and we must have the force. Okay, force for this tension in air. Okay, the Ft is equal to W. So Ft is, so W is, we can convert to M times by the G. Okay, the M plus the G, so we know that mass is equal to density by density of the block times the V and times the G. Okay, so you get the, put all the value here until you get the value of force of this tension. Okay, force of this rope. Now we look at the completely immersed in water. Okay, so we know that completely immersed in water, they must include the W. Okay, because this is immersed in water, so it must include the weight of this block. Okay, they must have the FB. Okay, they must have the buoyant force here. Okay, that occur to this weight of this block, and also the FT. So you must have the equation for this FT. So FT plus the FB, because go to upward. So the arrow is the upward, so this plus. Okay, so FT plus the FB is equal to this is W. Okay, so there's the W here. So they must have the, maybe you can use as, because the W is negative, so the downward. So maybe you can follow FT plus FB minus by W is equilibrium as the 0. Okay, so you can change to this one, or you can change. So just put the Ft is equal to W minus by Fb. Okay, it's okay. So you get to get the Ft. Actually, this is to find the Ft. So you get the value of this. Density W is the density of block times by the V volume and times by the G, minus by the density of seawater times by the Vg. Okay, just put the value here until you get the Ft is 6003.72 Newton. Okay, so this is for the immersed in the water and the submerged in the water and immersed in the air. Okay, so this is example 2.16. Okay, the figure shows a metal pipe object 2 hanging by a thin cord for the floating wood. Okay, the wood block has a specific gravity as G1. Okay, so find the mass M2. To find the mass of the 2 here, object of M2 of the metal pipe and the tension T. Okay, in the cord, to tension T of the cord. So free body diagram of the wood block here. Okay, so we know that they have the body diagram of the block. So wood block, so they have W and they will have the FB. Okay, so they have also the T. Okay, so this is the concept for free body diagram of the wood. Okay, for equilibrium, so you must use the T. Okay, FB is plus, it actually is negative here. Okay, so they gave you the T here. Okay, so to get the T, so just put all the value here until you get the T is 0.1104 Newton. Okay, so this is for wood block. Now we look at the metal part. Okay, metal part is at the 2. Okay, they have the W here, weight of this metal part, and they must have the FB. Okay, because this is immersed to the water, so they have the FB. Okay, and also the T. Okay, so for equilibrium, so you must know that W is equal to FB plus the T. Okay, so we just put the equation and put the value and we get the W. Okay, the W of the metal part. Okay, so therefore mass of the metal part is mass is equal to W divided by the G. So you get the value of 17.85 gram for this weight of metal. So now we look at the example 2.17. Okay, the height of the portion. You want to find the height. Okay, height of the height H, to find the H of this block. Okay, so now we just look at the here. So we know that they have the W and the FB here because this is submerged in the water. So you must use the weight of this ice block is density of body times by the G times by the V. Okay, and the density of fluid. Okay, so use this equation and put all the V submerged is W times by the L times by the H here. Okay, because the volume. Okay, volume for this block. Okay, so just put here and just put all the value in this equation. So until you get the H is 88 centimeter or 0.88 meter. So this is actually you just use the equation. Okay, you just use this equation and this equation. Okay, until you get this value. Okay, now you will just go through to the stability. Okay, after we learn more on buoyancy force, so you must know the stability. Okay, so the stability of immersed and floating bodies. Okay, so for floating bodies such as ship here, okay, stability is an important consideration for safety. Okay, so this is stability. So the rotational stability of an immersed body depends on the location of the center of gravity, G of the body, and the center of buoyancy, B, which is the centroid of the displaced volume. Okay, this is stable. Okay, when the G and W at the same place, and the B at FB and the B is this one. Okay, so this is neutrally stable. Okay, and this is unstable. So you can explain briefly based on this figure for stability. Okay, so the image of floating body is always stable if body is bottom heavy, where center of gravity G is directly below the center of buoyancy B. So maybe the G is below from the B. So this is stable. Okay. So now we look at the under-immersed bodies. A floating body may still be stable when G is directly above B. This is because the centroid of the display volume shift to the side to a point B during the rotational disturbance, while the center of gravity G of the body remains unchanged. Okay, actually the stability is more on theory. Okay, this is stable. Okay, when the FB and the B are the same place here and the W and G here. Okay, so this is stable. This is concept for ship. Okay, so this is also stable. So this when M and the B here and G here is this one overtuning moment, so this is unstable. Okay, if point B is sufficiently far, these two forces create a restoring moment and return the body to the original position. So a measure of stability for floating bodies is the metacentric height GM, which is the distance between the center of gravity and the metacenter M. Okay, so metacenter M ni, okay, metacenter M is the intersection point of the lines of action of the buoyant force through the body before and after rotation. Okay, so this is the more on stability, stable or unstable. Okay, so a floating body is stable if point M is above point G. If point M here, okay, is above point G. So if stable, so maybe point M is above the point G here. So M at the metacentered here. Okay, the above at the point G, and thus GM is positive. Okay, a floating body is unstable if point M is below point G. If the M is below point G, so the GM is negative. So this is unstable. So we use this equation. Okay, mg is equal to mb minus by bg, or to get the mg, so we get the I inertia divided by the volume submerged minus by bg. Okay, a floating body is stable if the body is bottom heavy and thus the center of gravity G is below and the centroid B of the body, or if the metacenter M is above point G. So however, the body is unstable if point M is below point G. So this is the theory for part of stability. So you can explain more on this stability if in your test or in your final ask you to explain, okay, to explain more about stability. Okay, so now we look at the example here. A block of wood, okay, square in cross section, and we have the side view here and the end view here to get the stability. Okay, so we know the side view and the end view here, so we know that the W and FB. Okay, and for equilibrium, so you must know that FB is equal to W. Okay, and we know that the GM is 1 over V minus by BG. Okay, so FB is density of water times by the volume times by the G. And we get the W. Okay, we know that W is given as, okay, the weight. Okay, weight is 318. Okay, that's why you get the 318 here. Okay, and just put the 0.6 times by the 0.3 here. Okay, and times by the D. Okay, we don't know the D. Okay, we want to find the D. So the rotation about transverse axis is using the GM to get the stability. So you just put here the value here, and we know that it's possible positive. Okay, if we use the B as 30 cm, okay, and the H, okay, the H is 60. Okay, so rotational about longitudinal axis, we use the B as a 60 and the H is this one. Okay, this is more rectangular. You must use the inertial moment here using the rectangular. So based on this one. Okay, so you get the value here. And this negative. So if negative is unstable. Okay, so the stable value is this one. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.